In this video, we will discuss the Aldol reaction. The Aldol reaction builds off of what we've learned about aldehydes and ketones acting as electrophiles, reacting with nucleophiles at the carbonyl carbon. In the Aldol reaction, the nucleophile is an enolate under basic conditions or an enol under acidic conditions. This is an incredibly important and powerful transformation in synthetic organic chemistry. The carbon of the enolate or the enol makes a bond to the carbon of the aldehyde or the ketone. So a carbon-carbon bond will be made. However, as you might guess, enolates and enols come from aldehydes and ketones. So aldehydes and ketones are going to be acting as both the electrophile and the nucleophile. It's okay, don't panic. We're going to walk through it step by step. Let's get started. The learning goals for today are to be able to provide a complete curved arrow mechanism for the aldol addition reaction under both base and acid catalyzed conditions. To provide the complete curved arrow mechanism for the formation of the aldol condensation product. So there seems to be an aldol addition product and an aldol condensation product via an E1CB elimination. Ooh, exciting. We're going to learn a new pathway for eliminations. Again, under both basic and acidic conditions. All right, so we're noticing here these reactions can happen in basic solution and acidic solution. And then we'll predict the products of all kinds of aldol reactions. There'll be a few variants. Just straight up, this is called a self-condensation. So between an aldehyde or ketone and its own enolate. A crossed aldol, meaning two different carbonyl species react. And then finally, intramolecular. Ooh, that means we're going to be making some rings today. Let's get started. Before we hop right in, let's be sure that we remember some terms, some definitions. So please draw acetophenone. Acetophenone is a ketone. Acet means that there's going to be a 2-carbon piece that includes the carbonyl carbon. Phenone means there is a phenyl group also bonded to the carbonyl carbon. So draw acetophenone. Obviously, you need to combine these two pictures, and it's carbonyl, enol, and enolate forms. Here is acetophenone in its carbonyl form. It is electrophilic at the carbonyl carbon, like most or all aldehydes and ketones. The enol form is a tautomer. It's a constitutional isomer. So one of the hydrogen atoms at the alpha carbon. And now acetophenone has 2 alpha carbons, but this one has no hydrogens. So we can't remove a hydrogen from that alpha carbon, so we're going to ignore it now. But this alpha carbon has a hydrogen on it. That hydrogen moves from carbon to oxygen. Here it is in the enol. So the enol is a tautomer, a constitutional isomer of the carbonyl. Enol is nucleophilic at the alpha carbon. It now behaves like a alkene in a way, right? The ene means alkene, so it's nucleophilic at the alpha carbon. We can understand that by this resonance structure. I'll look at that carbon ion. All right, so even though this is the minor resonance structure, it is still significant, and we will see enols and enolates. So enolates are typically formed under basic conditions. You can see that the OH, the proton, has been removed. And as you might expect, it is an even stronger, more reactive nucleophile at that alpha carbon because there's a negative charge. It's anionic, so there's going to be more negative charge at that alpha carbon. Now that we have the terms down, let's keep going. We have a little more review to do. So draw generic examples of all these species, do the labeling, and then let's get going. As we know, aldehydes and ketones are carbonyl-containing functional groups. Here's the carbonyl. The ketone has 2 alkyl groups off the carbonyl carbon, whereas the aldehyde has 1 alkyl group and 1 hydrogen. The generic examples are drawn up top. And here's a specific example of an aldehyde. This is benzaldehyde, where there's a phenyl substituent and a hydrogen off the carbonyl carbon. Let's label the carbonyl carbon in yellow. It's true for all these species. The alpha carbon is adjacent to the carbonyl carbon, Aldehydes have one alpha carbon, whereas ketones will have two. Aldehydes don't have a carbon adjacent on one side of the carbonyl, so it won't have an alpha carbon there. An alpha beta unsaturated ketone, let's check out its alpha carbon. Let's check out its beta carbon. That's adjacent to the alpha. So alpha beta. Alpha beta unsaturated ketones have unsaturation, a double bond between the alpha and beta carbons, conjugated to the carbonyl, meaning that this molecule is represented by resonance structures. We know that alpha beta unsaturated ketones are electrophilic at the carbonyl carbon, like all aldehydes and ketones, and also at that beta carbon. And we can rationalize that through this resonance structure. Of course, we can point out that the alpha beta unsaturated ketone here has two alpha carbons. We can call that one alpha prime. We don't particularly care about it right now because it's not involved in the unsaturation, so we were ignoring it. Do aldehydes and ketones contain acidic hydrogens? Often. Looking at the top of the screen, if the alpha carbon has hydrogens bonded to it, they are in fact acidic. If treated with a base, the alpha carbon can be deprotonated. That is because the conjugate base is stabilized by delocalization of charge. Oh, and what have we formed here? What have we formed here? Oh, an enolate. Huh. Remembering that aldol reactions today are going to be between enolates and aldehydes and ketones in their carbonyl form. So this is all going to be important. All right, enolates are going to be nucleophiles. We'll just write that down one more time. So just this acidity of the alpha carbon is going to give us the enolate nucleophile partner in the aldol reaction. We'll get there, don't worry. We'll talk about the pKa's of aldehydes and ketones as we continue in the lecture. Let's just consider one more question as we get going, which is what is the stronger electrophile, an aldehyde or a ketone? To answer this question, we can recall hydrate formation, where the aldehydes or ketones were in equilibrium under either acidic or basic conditions. So here I've put base catalysts. They were in equilibrium with the hydrate form. Do you remember which of these functional groups, aldehydes or ketones, was more reactive in hydrate formation? Yes, aldehydes typically form the hydrate with equilibrium constants greater than 1, while ketones typically formed it with equilibrium constants less than 1, meaning they favored the unreacted carbonyl form. So we can use this data to rationalize aldehydes are more electrophilic than ketones. We'll keep all of that in mind. We have one more little question here, which is this. Consider which water-related species exist in appreciable amounts in aqueous base, such as sodium hydroxide, and aqueous acid, let's say such as hydrochloric acid. In aqueous base, there is appreciable amounts of hydroxide and water. In aqueous acid, there are appreciable amounts of hydronium and water. Now, of course, we know in all aqueous solutions, there's some hydronium and some hydroxide and plenty of water. But we're just thinking about appreciable amounts here. Like what is significant, what species are going to exist in high enough concentrations to be reactive. So in base, we have hydroxide, and this is going to act as a base. Water is going to act as an acid or a proton source. In aqueous acid, the hydronium is acidic. It's going to act as the proton source. In water, if deprotonation occurs, water is going to act as base. All right, we need to keep all of this in mind. That was a lot. You might take it from the beginning again. Carbonyl, enol, enolate forms of aldehydes and ketones, vocabulary terms, and thinking about what species exist in aqueous acid and base. And of course, aqueous acid and base are going to be important here because as we gathered from the learning goals, this reaction that we're learning today, the Aldol reaction, can take place under both base and acid catalyzed conditions. So that's why we talked about this briefly. All right, that gigantic preamble in hand, let's get started. For real this time.
This is an example of an aldol reaction. take a look at it. So we're treating an aldehyde, and this works with a ketone as well, with a base. And although it's not specified, this is under aqueous conditions, so there's also some water around, so that's useful to keep in mind. And you can see that 2 molecules of the aldehyde have come together. So this is a dimerization reaction. So we have 2 molecules of the aldehyde that have come together. You can see we've made a new bond. So why is this reaction important? We can answer that question right now. We've made a carbon-carbon bond. How can we recognize the Aldol reaction? You're going to look at the functional groups, how you recognize any reaction. So we have the aldol addition intermediate. Look at the functional group here. This is called a beta hydroxyaldehyde. So here's our alpha carbon. The alpha carbon is adjacent to the carbonyl carbon. And then next to the alpha is beta. So we have a beta hydroxyaldehyde. If you started out with a ketone, you'd have a beta hydroxy ketone. This also works with ketones. You're looking for that beta hydroxy relationship to whatever the carbonyl is. And then finally, under these reaction conditions, the aldol addition intermediate can continue to undergo reaction and make what we call the aldol condensation product. One day I'll fix the typo on this slide. It's called the aldol condensation product because a molecule of water is also released. You can see it. It's right here. So this molecule of water is eliminated. And instead of having a beta hydroxyaldehyde or ketone, you have an alpha beta unsaturated aldehyde. Or if we started with ketones, you'd have a ketone. Let's take a look at the mechanism for the aldol reaction. When the aldehyde is exposed to a base, such as sodium hydroxide, the alpha carbon is deprotonated. Recall in the past that you've learned that deprotonating the alpha carbon of an aldehyde or a ketone generates a stabilized enolate. So we'll deprotonate the alpha carbon and draw this representation of the enolate. You can see now you have a lone pair adjacent to a pi bond and that you should consider resonance structures. We can draw a resonance structure for this conjugate base that looks like this. Once we recognize that this conjugate base is stabilized by delocalization of charge, we realize that the alpha carbon is relatively acidic. In fact, the pKa of the alpha carbon of an aldehyde is around 18. Keep in mind we're talking about the pKa of an alpha CH. We are not talking about the aldehyde hydrogen itself, the one directly bonded to the carbonyl. This hydrogen directly bonded to the carbonyl is not acidic. It's the alpha hydrogen that is acidic. This is, we initially drew the minor resonance structure of the enolate, and we came to the major resonance structure of the enolate where the negative charge is shown on the oxygen, as it's more electronegative than carbon. From here we can show how this electron-rich enolate, it's going to act as a nucleophile, can react with another molecule of the aldehyde. Remember, we already identified this is a dimerization reaction. So let's look at that one more time. We have 2 molecules, 2 units of the aldehyde. In the product, we can see that we've made this bond, okay, in both cases. So we've made a bond between the alpha carbon of one of the aldehydes and the carbonyl carbon of the other aldehyde. We're going to go ahead and do that right now. So the second aldehyde in the carbonyl form, it's going to act as the electrophile. The enolate, you're going to come down, reform your double bond. These electrons are going to go from the alpha carbon and attack the carbonyl carbon of another aldehyde. That's going to generate the following intermediate. The way I've drawn it, it's going to look a little turned around from the picture that I have right here in the box, but that's okay. Need to get used to seeing molecules in different perspectives. Here we are. Right now you can see that we have what looks like it's almost a beta hydroxy aldehyde. We just need to protonate the alkoxide here. So we're going to go ahead and do that now. Now we need to protonate the alkoxide. It means we need to use an acid. Look at our conditions. We're an aqueous base. So we have significant amounts of hydroxide and water. When we need a base, we're going to use the hydroxide. When we need an acid or a proton source, we're going to use water. We're going to use water here to protonate, and that brings us to our aldol intermediate. So let me just, to have the structures rotated, let me just do a little bit of creative highlighting here to show you what's going on. So this section, that's right here. these carbons and oxygen, they're right here. So that's the aldol addition. Now it can be hard for you to predict whether or not you're going to see the addition intermediate, so this intermediate, or if you're going to go all the way to the condensation. So if I'm having you predict, I'll have to give you the molecular formula of the product because it's hard for you to tell whether or not it stops or it continues on. Now that we know how to form the aldol addition intermediate, we're going to look at forming the aldol condensation product. Before we do that, I just want to point out that to make the aldol addition intermediate, there were 3 steps. So we had a proton transfer reaction. We recognized sodium hydroxide was a base, and we used it as a base to deprotonate something. After the proton transfer reaction to make the enolate acted as a nucleophile reacting with an aldehyde. This is a nucleophilic addition to that pi star CO of the aldehyde. After that, we had another proton transfer reaction, this time where we had the alkoxide species acting as a base, and we had water acting as our proton source, our acid. Even though water is a weak acid, it can act as a proton source in basic solution. Now let's take a look at formation of the aldol condensation product. As we mentioned previously, this looks like it's pretty straightforward. It looks like we're just performing an elimination of water across the alpha and beta carbons. And we're in the presence of a strong base, so you remember from the first semester that in the presence of a strong base, any 2 elimination can happen. So we're very tempted to consider any 2 mechanism. But I want you to recall our discussion of E2 reactions on alcohols in the first semester of organic chemistry. The proposed mechanism here would be the strong base, be it hydroxide or ethoxide or whatever you have, would deprotonate beta to the leaving group, and then hydroxide would leave as the leaving group. Hopefully you recall this does not occur, and there are several problems with this. First of which is that hydroxide is a poor leaving group. Poor leaving group meaning it is a strong base. It is the conjugate base of a weak acid. So you look at its conjugate acid, you see its pKa is 16, that's a weak acid. We have defined hydroxide as a strong base, and it's a poor leaving group. So that's one reason this E2 elimination of alcohols does not occur. The second reason is that the most acidic proton in this molecule is simply that proton of the alcohol. Its pKa is about 16, as you know, and if you treat this molecule, this alcohol, with sodium hydroxide, all that's going to happen is that you're going to make the alkoxide, and you're not going to have an E2 elimination. So I want you to keep that in mind as you consider the problem at hand, going from the aldol addition intermediate to the aldol condensation product. This is not going to be a simple E2 elimination. That said, we can use our chemical intuition to move forward and propose a mechanism. Now we're in the presence of base, so we want to look at our aldol addition intermediate, which I've redrawn over here, and think about what are the acidic protons in that molecule. So there are 2 that jump out. This one we just talked about, the alcohol proton, that's certainly an acidic proton. But there's one more. Hopefully you came up with it while I paused. It's the hydrogen on the alpha carbon. Remember when we went through the aldol addition, we started by deprotonating that alpha carbon of the initial aldehyde with base. And we can do that again. And we can do that because it's going to make a stable enolate. This is actually the only reason why this elimination occurs. It occurs because we're making the stable enolate. I'm going to go ahead and draw these arrows going directly to the major resonance structure of the enolate. That is your goal too. You want to be able to go directly to the major resonance structure of the enolate. So here we go. From here, and I should mention all of these steps are equilibria. From here, we can reform the nice strong CO double bond. These electrons are going to scoot over between the alpha and the beta carbons, and we will expel hydroxide. Well, look at what we've done here. One more time. We've reformed the strong CO double bond, The electrons that were between the carbonyl carbon and the alpha carbon, they've moved over and they've formed the alpha beta double bond. And then we've expelled hydroxide, and that's great because hydroxide is not in the product. So let's go ahead and draw that out. So my arrows result in this product, which is exactly what I have above. These two molecules are the same, and a molecule of hydroxide. Now, you might say to me, and you would be correct, wait a second, you just said that hydroxide is a poor leaving group. It is. It is a poor leaving group. However, this reaction occurs, and it's by a different mechanism. This is not an E2. We've deprotonated and made an enolate, and then the enolate reforms the more stable carbonyl. Look at what you're doing. You're converting a CC double bond to a CO double bond. CO double bond is more strong. So you're reforming the CO double bond and expelling hydroxide. And so the thermodynamics this time are in your favor. So the name of this mechanism is called an E1CB. So E1, I'm going to write that somewhere. This is an E1CB, where it's E1 and that there's a unimolecular rate law. So this would be the rate determining step. And then the CB, there's no comma here. The CB stands for conjugate base. And so the CB stands for conjugate base. And again, this elimination of hydroxide only happens because it goes through a stable conjugate base. This is the exact mechanism that you need to draw for formation of the aldol condensation product. Let's run through this mechanism one more time. This time we'll look at the treatment of a different aldehyde under the same conditions. And those conditions are treatment with aqueous sodium hydroxide. So you should pause and see if you can predict the product of this reaction. So I want the condensation product, be an alpha beta unsaturated aldehyde. Pause and predict. Welcome back. Your condensation product should look something like this. So what we have happening here, two of these aldehydes condensing. We form the new bond. Again, between the alpha carbon of one molecule of that aldehyde and the carbonyl of the other aldehyde. This molecule, the one that reacted by its carbonyl carbon, that was the electrophile. The one that reacted by its alpha carbon was the nucleophile. Now let's get into the mechanism. Again, I think you should pause and try it yourself. Sodium hydroxide is a strong base, and under these conditions, it can deprotonate the alpha carbon. This is an equilibrium. The equilibrium constant is around 1, and that's because the pKa of this aldehyde is around 17, probably a little lower for this one. Water, the conjugate acid of hydroxide, has a pKa of about 16. So the equilibrium constant is about 1. So we're going to go ahead and deprotonate the alpha carbon directly to the most stable resonance structure of the enolate. This enolate is an electron-rich species. It has a negative charge. It's nucleophilic on the alpha carbon. And really thinking about the resonance structure, the minor resonance structure, helps you conceptualize why it's nucleophilic on the alpha carbon. You can see the charge is shared between oxygen and carbon. So now that we have our nucleophilic partner for this reaction, it's going to interact with another molecule of itself, but this molecule is still in the aldehyde form. From here, we're going to come down, reform the CO double bond. That's going to give me, look up top, it's going to give me this CO double bond. The alpha carbon now is going to attack the aldehyde carbonyl. So now we're making, look up top, this bond, and that breaks the pi bond. So what we'll have now looks like this. I'm going to try to leave the molecules in about the same orientation they were previously. Okay. Now from here, what's the stress on this molecule? Well, the stress is the negative charge. As usual, I got a little bit excited, so let's back up. Let's point out where all the atoms are. So we have our new carbon-carbon bond between the alpha carbon of this enolate and the carbonyl carbon. So this carbon right here, that becomes what I'm labeling as beta, because now the carbonyl The only remaining carbonyl is kind of dictating the nomenclature here. So the carbonyl carbon of the second aldehyde, this one, it's becoming the beta carbon in the product, right? We discussed that. All right, now let's get to the stress. So the stress is the negative charge on oxygen. That's basic. It's going to react with an acid. The acidic species in water, basic water, is just water. Hydroxide is the base, and then water is the acidic species. This is our proton source. Mildly acidic, but good enough in this case. You know, all of these steps are equilibria. All these steps are reversible. So now we form the aldol addition. I'm going to go ahead and abbreviate the aryl groups as phenyl. We've made the aldol addition product. This is that beta hydroxyaldehyde. So I asked you to draw the mechanism all the way to the condensation product. Remember that this reaction occurs by this E1CB mechanism. The first step of that is that the hydroxide deprotonates alpha to the carbonyl. That proton alpha to the aldehyde here, it's acidic, and that's how I knew to deprotonate it. That generates an enolate. An enolate is a stable conjugate base. From the enolate, we reform the strong carbon-oxygen double bond. These electrons slide over now between the alpha and the beta carbons to make that alpha-beta double bond. And when that happens, hydroxide leaves as a leaving group. So we get our product, and we get a molecule of hydroxide. That is another example of an aldol condensation reaction, and you should go and do a lot of practice now.
Now that we've practiced drawing the complete curved arrow mechanism for the aldol addition and condensation reactions, let's practice applying the overall pattern of aldehyde self-condensing to form either the addition or condensation product. For this exercise, we will examine the following 4 questions. You should predict the missing product or the missing reactant for these addition and condensation reactions. And because for the predict the product problems, it's hard to know whether or not the reaction stops at the addition or continues on to the condensation, I've given you the molecular formula so that you can sort that out yourself. I very strongly suggest now that you pause and try these problems on your own. All right, applying the pattern that I've diagrammed above, we can see there are 2 carbons for this aldehyde. Carbon 2 is the alpha carbon. This is the formula of the beta hydroxyaldehyde, so the addition product. So I imagine connecting the alpha carbon of one molecule of acetaldehyde with the carbonyl carbon of another molecule of acetaldehyde. Now, obviously, this goes via the enolate, so really be connecting like this. But remember, you're not drawing a mechanism here. You're just applying the pattern so that you can predict the product. And to be really efficient about this, you want to be able to do it without drawing the mechanism. So that's carbon 2 and 1 of the carbonyl, the electrophilic acetaldehyde, and this is carbon 2 and 1 of the nucleophilic acetaldehyde. Let's try for the next example. Whereas the aldehyde only has 1 alpha carbon, ketone has 2 alpha carbons. Luckily, this alpha carbon doesn't have any hydrogens on it, so we don't have to worry about an enolate being formed from that carbon. So an enolate at the only alpha carbon that has hydrogens will make a bond to a molecule of itself that is still in the carbonyl form. And if we want, we can draw this out as the enolate if that helps us. When this bond is formed, the carbonyl is reformed. So here's this first molecule, the one that acted as the nucleophile. Here's the other molecule. The alpha carbon is going to make a bond to the carbonyl carbon. So this was the carbonyl carbon. All right, that's what it would look like right after the addition step. Take a look at the formula, work it out. This is actually the condensation product. Now you want to be careful. You can't really just count the number of oxygens because like what if there was another oxygen somewhere in the aldehyde and ketone that was not part of the carbonyl? You can get tripped up. But this is the formula for the condensation product. So now we're going to just imagine dehydrating between the alpha and the beta carbons. So I'm going to go ahead and do that. Put in the alpha beta unsaturated ketone, the condensation product. Excellent. Now let's try to predict the reactants problems. These might actually be a bit easier. We want to identify the beta hydroxy ketone or alpha beta unsaturated aldehyde because that tells us where to disconnect. So we're disconnecting between alpha and beta, right? The alpha carbon had been the nucleophile, the beta carbon had been the electrophile, the molecule in its carbonyl form. I believe when we do those disconnections, we can see that. The first example is a self-condensation of cyclopentanone, and the second example is a self-condensation of this aldehyde. Here we go. Map that on there. There's another. Same as cyclopentanone. This just takes practice. We're just applying the overall pattern. So far, all of the examples that we have considered have been self-condensation. Look over on the left side of the screen. One molecule of the aldehyde or ketone in its carbonyl form, condenses with another molecule of itself, but that molecule is in the enolate form. And we know that under basic conditions, the carbonyl and the enolate will be in equilibrium with one another. Carbonyls are electrophiles, enolates are nucleophiles, so they can condense, they can react, and that's what the aldol addition reaction is. So far we've seen these self-condensations. We're going to move on now to the crossed aldol. So self-condensation, check. Now we're going to move on to the crossed aldol, and this is when the nucleophile and electrophile will come from two different carbonyl compounds. So here's an example of a crossed aldol reaction. I would like for you to propose a complete curved arrow mechanism before you listen to me explain it. As always, we begin by identifying the functional groups and the reactants and the products. We take a look at the conditions and ask, what are you? We can see that the conditions are aqueous base. The alpha beta unsaturated ketone coming from reaction of an aldehyde and ketone under aqueous base suggests an aldol condensation. We know that the bond between the alpha and the beta carbon was the bond that was the key bond made in this reaction. The alpha carbon of the product was the nucleophile in the aldol addition step. The beta carbon in the product came from the electrophile, the carbonyl compound, so the compound in its carbonyl form that reacted with another carbonyl compound, aldehyde or ketone, but in the enolate form. Using that knowledge, let's propose the complete curved arrow mechanism. Since this ketone reacted as the enolate, we will generate the enolate by deprotonation with sodium hydroxide. Because the pKa of the ketone is about 20 and the pKa of water is about 16, this proton transfer reaction does have an equilibrium constant less than 1. However, the enolate is formed, and when the enolate is formed, it can react as a nucleophile at the alpha carbon. There is an electrophile in solution. That electrophile is the aldehyde. They react in a nucleophile addition step, which we specifically call an aldol addition because the nucleophile is an enolate, to generate this intermediate. Let's map on all the atoms of the enolate and the atoms from the aldehyde. We will also identify the key bond that was just formed. This intermediate containing a basic alkoxide oxygen will be protonated by water. In basic solution, water is the proton source and hydroxide is the base. The equilibrium constant for this step is about 1. This proton transfer reaction generates the aldol addition intermediate. This beta hydroxy ketone is acidic at the alpha carbon. Of course, it's also acidic at the hydroxyl, but if we deprotonate there, that takes us back to this intermediate, and it is not productive in getting us towards the product. Both the hydroxyl hydrogen and the alpha carbon are acidic. Both of them are deprotonated in the presence of hydroxide. We will only worry about the deprotonation that gets us to the product. So generating the enolate in this E1CB mechanism results in this intermediate. This intermediate collapses, so the carbonyl bond is reformed. That's all I mean by that. So the carbonyl bond is reformed. These pi electrons slide over. Hydroxide is expelled. Hydroxide is not a good leaving group, but when hydroxide is expelled, the strong carbonyl double bond is reformed, and that is the driving force for this reaction. In addition to this step being favored by entropy, right? We've formed two things from one. Excellent. Now it's your turn to analyze a crossed-Aldol reaction. Pause and predict the possible products of this reaction. When these aldehydes are treated under basic aqueous conditions, both can react to yield their enolates in proton transfer reactions. Both of these aldehydes have alpha carbons with hydrogen atoms. These deprotonations generate two nucleophilic species. These nucleophilic enolates will react with electrophiles in solution. And there are two possible electrophiles that each one of these enolates can react with. What are those, you say? Well, the two aldehydes we started with in their carbonyl forms. This yields four possible products. Two of the products represent self-condensations, such as the self-condensation of butanol, represented on the left side of the screen. On the right side of the screen, we see the self-condensation of acetaldehyde. And in the middle, there are the two crossed aldol products, where butanol attacked a molecule of acetaldehyde in its carbonyl form, and acetaldehyde attacked a molecule of butanol in its carbonyl form, as shown. Well, this crossed aldol is a mess. Imagine trying to separate these four products. Which technique would you use? Could you use extraction? No, you might be able to use distillation, but I bet some of these molecules have pretty similar boiling points. This result, getting a mess, getting four possible products, is pretty common for cross-aldol reactions. Cross-aldol reactions that work, those examples are pretty few and far between. So how can we understand why this cross-aldol reaction, it worked? It only made one product. This worked so well, making one major product, because the aldehyde has no alpha CH bonds. So here's it. Aldehydes only have one alpha carbon. Here it is. There's no alpha CH. You might be thinking, well, so what? Well, that means it can't make an enolate. Okay, it cannot make an enolate, and so it can only react as the electrophile in this transformation. It can only be attacked by an enolate. It can't make an enolate. And now the ketone, it certainly has alpha CHs, and the alpha carbons are the same, so it's only going to make one type of enolate, which is this enolate. And now this enolate, it serves as the nucleophile. You might say, okay, wait a second. There's two potential electrophiles. The enolate could attack itself, or it could attack the aldehyde. Well, what did we discuss way back here? What is the stronger electrophile, an aldehyde or a ketone? Aldehydes. So that's how this works. That's why this makes one product, this specific cross-aldol reaction. Because this enolate nucleophile, although it could attack either of these compounds in their carbonyl form, the aldehyde is more reactive. So the aldehyde is the major electrophile, and so this is the major product of this reaction. There probably is some self-condensation product, but it's minimal since the aldehyde is so much more reactive. So for this cross-aldol to work, there is one electrophile and one nucleophile, which is the enolate of the ketone. Keeping all of this in mind, propose a synthesis for the following product via a cross-aldol reaction. Please pause and give it a shot. Let's identify the alpha beta unsaturated carbonyl compound. Once we've done that, we can identify the bond, the key carbon-carbon bond that was made in this process. The alpha carbon of the final product acted as the enolate in the key carbon-carbon bond forming step. And this carbon, which is the beta carbon in the product, it served as the electrophile. It was in its carbonyl form in the key carbon-carbon bond forming step. So we might propose taking these two ketones, treating them with sodium hydroxide to yield the desired alpha-beta unsaturated ketone via an aldol condensation reaction. Let's think about what is required for a successful cross-aldol reaction, where success is defined as one major product. There must be one enolate and one major electrophile. All I mean by that is that we saw we could exploit relative reactivity. And when there was an aldehyde and a ketone, typically the aldehyde would be more reactive. However, if we look at the two ketones being proposed here, we see lots of different types of alpha carbons with alpha hydrogens. And so two enolates would be possible when those two ketones are treated with sodium hydroxide. Those two enolates are the desired enolate of acetophenone, right? This is the one that we're proposing. But just because that enolate is desired, we can't stop acetone from reacting with sodium hydroxide. If both of these ketones are present, then both enolates are going to be formed. The two ketones have similar acidities, and they both have acidic alpha carbons. Two enolates are possible, so we're not going to get a clean reaction to form only one major product. Two enolates are possible, not to mention the fact that there's going to be two carbonyl compounds that each of these enolates can react with. They can undergo self-condensation. They could also undergo cross-condensation, so with each other. So I'm showing the self routes on the ends, the crossed aldols in the middle. And again, we're going to be in this situation where there are four products possible. Now, once we verbalize the problem, the challenges that two possible enolates are generated and they can react with two possible carbonyl electrophiles, we can start to think about what the solution might be. The problem is arising since we're taking both carbonyl compounds at the same time and treating with a base to form the enolates in situ. Instead of that, what if we could take acetophenone by itself, generate the enolate, so there's no more acetophenone, it's all enolate, and then take that enolate and treat it with acetone. So we'd have one nucleophile and we'd have one electrophile, because once we've completely generated the enolate, then there's no more of the acetophenone carbonyl compound. So there's no more chance of self-condensation. Well, that sounds great, but how do we completely generate an enolate? Can we do this? Have we done this before? Yes, we have. We can treat with lithium diisopropyl amide. Lithium diisopropyl amide, LDA, is a much stronger base than hydroxide. Its conjugate acid is an amine, which has a pKa of about 35. The equilibrium constant for this deprotonation is on the order of 10 to the 15. Whoa, that's much, much greater than 1. And of course, that's just using the generic pKa value for the alpha carbon of a ketone, which is 20. So the enolate of acetophenone can be generated quantitatively at pretty low temperatures because LDA is really reactive. under these conditions. Then the enolate can be treated with the desired electrophile. Now the intermediate of this step will look like this. Okay, there's no proton source. So this is the intermediate of reaction of the enolate with acetone, with the electrophilic carbonyl compound, because there's no proton source around. So for the rest of the aldol to occur, for the condensation part to occur, we do need an aqueous workup. And then the product will be generated in high yield. This is the only expected product of this aldol condensation reaction. Sweet, let's use LDA all the time for crossed aldols. No, not sweet. Do not start invoking LDA all the time. There are only very specific examples when you should invoke LDA. Lithium diisopropylamide is a very reactive base, and you cannot just use it in any context you want. It can cause side reactions and other undesired consequences. So we will only be using LDA for crossed aldol reactions between ketones. LDA is not really compatible with aldehydes, so we're only going to use LDA for the crossed aldol reaction between ketones. We've already learned that LDA can be used to make kinetic enolates. For example, in the case of asymmetric aldehydes, to generate the less stable enolate, so to deprotonate selectively at the primary alpha carbon rather than the tertiary alpha carbon, which generates this disubstituted alkene instead of the more substituted, more stable tetrasubstituted alkene, we would use just over an equivalent of LDA just to completely guarantee deprotonation at the last Hender carbon, and that's because LDA is enormous. It is a very bulky base. We have learned that you can also actually generate the thermodynamic enolate quantitatively with LDA as well, and to do that, we just use a little bit less than one equivalent of LDA, and what that does, it first generates the kinetic enolate, but since there's still going to be some unreactive ketone around, there is equilibration to the more stable thermodynamic enolate. Okay, so we can use LDA with asymmetric ketones to make either the kinetic or the thermodynamic enolate. And then finally, the last acceptable use of LDA is to deprotonate alkynes to make acetylide ions. We encountered this in Organic Chemistry 1. It's not the most common base for this application. More typically, sodium amide is used for this application, but LDA can be used to deprotonate alkynes as well. And then these acetylide ions can be used as nucleophiles with various electrophiles, such as alkyl halides or epoxides. You need to think about LDA as an axe. Sometimes you need an axe, sometimes you need a scalpel. Only use LDA when you need an axe. It is really, really reactive. And it was a great solution to this crossed aldol problem between ketones. We learned that we either need to use LDA for crossed aldol between ketones, or sometimes you have a non-enolizable aldehyde, which will just act as the electrophile, and then a ketone of some type that will just act as a nucleophile. That was the first example we saw, and that was okay for the crossed aldol. Let's meet our last goal, which is to predict the products and draw the complete curved error mechanism for intramolecular aldol condensations. Also, I'll quickly point out, we've discussed base catalyzed reactions. We have not tried the acid catalyzed mechanism, so that will be coming up as well. Okay, here we go. Provide a complete curved error mechanism for this reaction. I'd say give it a shot yourself and then compare with me. We immediately identify the alpha beta unsaturated ketone product We suspect that that was generated by an aldol reaction, and we do see a ketone and an aldehyde starting material. Now, we're used to seeing hydroxide as the catalyst. In this case, we notice that there is ethoxide. That's okay. Ethoxide is similar to hydroxide. Instead of a proton, there's an ethyl group, and it can serve as the base catalyst. So ethoxide will do the deprotonating. It will act as the base. And we expect that ethanol, its conjugate acid, is simply here as a source of protons, that it will do the protonating, serve as the acid. It does appear that the ketone enolate right here has condensed onto the aldehyde carbonyl, and just given our analysis of the product. If that happens, if an enolate at the alpha carbon did attack the aldehyde carbon, that would generate a 1, 2, 3, 4, 5-membered ring. 1, 2, 3, 4, 5. That looks about right. Let's give it a shot. To generate the enolate, sodium ethoxide deprotonates the alpha carbon. Proton transfer step is reversible and does in fact favor the reactants of this elementary step. However, once the enolate is formed, it is nucleophilic, and that alpha carbon can attack the aldehyde that is in the same molecule. That aldehyde is next to it all the time. So intramolecular reactions like this are really quick. The nucleophile and electrophile are tethered to one another. This nucleophilic addition will generate the following intermediate. I know that when I draw these out, I'm doing it quickly and I already know what's going on. So it might seem like it's easy, or I think it's easy. It's not. You really do need to think about what's going on. Count between the atoms that are making the ring, so that gives you the ring size. And just take a minute and make sure that all the atoms are present and accounted for. And everything makes chemical sense. You do have a chemical intuition. Even if you don't think so, you do. I know you do, and it will help you. So trust your chemical intuition. Now from here, this alkoxide-like intermediate, does accept a proton from ethanol. Remember what we said at the beginning. Ethoxide is used for deprotonating, and ethanol is used for protonating as an acid. This generates the beta-hydroxyketone intermediate of the aldol addition reaction. We do notice, however, that the product is the alpha-beta unsaturated ketone, so the condensation step also occurs. The condensation step occurs by an E1CB mechanism, as we have discussed. Ethoxide deprotonates alpha to the carbonyl, generating the stabilized enolate. Now, just as before, when an enolate was generated, the equilibrium constant for this individual step certainly is less than 1, but once this enolate is formed, the strong CO double bond is generated. These electrons slide over and expel hydroxide, generating the final product. Take some time with this example. The steps are the same as for the intermolecular aldol reaction. The steps are the same. They're just happening within the same molecule. And it does make it more challenging. I agree. Intramolecular reactions always feel a bit more difficult to both identify and understand, but you have the tools to do it. Once you're comfortable with this example, we're going to transition to considering how aldol condensations can be catalyzed by acid. Finally, we're going to talk about how they can be catalyzed by acid. Remember what we said at the very beginning of the lecture? An aqueous acid, hydronium will be the proton source, and water will do the deprotonating. It will act as the base. I will lead you through this entire mechanism, but it would be really great if you could stop and try yourself. See what you can come up with. We know that an aldol condensation has occurred. We see the alpha-beta unsaturated ketone product. We know that the alpha carbon of the product was the nucleophile in the aldol addition. The beta carbon of the product was the electrophile. Under basic conditions, the nucleophile was the enolate. Under acidic conditions, the nucleophile in the aldol addition is the enol. We know that carbonyls are in equilibrium with their enol forms under acidic aqueous conditions, and it's no different in this case. So the nucleophile will be the enol, and the electrophile will actually be the protonated carbonyl compound. Those are the two big differences between the aldol condensation under base catalyzed conditions versus acid catalyzed conditions. We will first generate the enol. The acid in solution is hydronium. Any tosic acid or whatever the initial acid source was has long dissociated to generate hydronium. Now we can recall the mechanism for keto-enol tautomerization. That is what I am employing here. Protonate the carbonyl, and then once the carbonyl is protonated, deprotonate the alpha carbon. Remember, hydronium is the proton source, water will be the base. So in the second step is a proton transfer. We're going to use water to deprotonate the alpha carbon. And we're going to generate the enol. And I'm going to draw the curved arrows directly to the enol. Now, the enol, which will be the nucleophile in the aldol addition reaction, is present. However, we know that enols are less nucleophilic than enolates. They're less electron rich, right? So enols do not react with neutral aldehydes, at least not very quickly. And in fact, the aldehyde can be protonated by hydronium. When the aldehyde is protonated with hydronium, it is now electrophilic enough to react with the enol. Referring to the top of the page, there's an enol nucleophile and the protonated carbonyl electrophile. This is the main difference between the base and acid catalyzed aldol reactions. In base, it was an enolate and just the carbonyl, didn't have to be protonated. But in the case of the less reactive enol, it is the protonated carbonyl that is the active electrophile that is electrophilic enough to react with it. So here's our aldol addition step, where the alpha carbon makes a bond to the carbonyl carbon. This will generate a 1, 2, 3, 4, 5-membered ring. Orient yourself. Be sure you can see how this intermediate is formed from this nucleophilic addition. The protonated carbonyl compound undergoes deprotonation with water as the base, right? On acidic aqueous conditions, water will do the deprotonating to generate the neutral beta hydroxy ketone. That's the same aldol addition intermediate. The ultimate product of this transformation is the alpha beta unsaturated ketone, the condensation product. So water should be eliminated across the alpha and beta carbons to get to that product. Now, under base catalyzed conditions, this transformation proceeded via an E1CB mechanism. Under acid catalyzed conditions, it is thought that this proceeds via a more traditional or normal, if you will, E1 mechanism. First, the hydroxyl is protonated by hydronium to generate this intermediate where we can see water, which is a good leaving group. That's the big difference. Hydroxide is not a good leaving group, but water is. So this transformation, again, is thought to go through a more traditional or normal, however you want to refer to it, E1 via carbocations. And then now this carbocation intermediate undergoes electrophile elimination, or the second step of E1 elimination, to generate the final product. Voila, we did it. It's a bit messy, but you take a look at it, pause. We have drawn the mechanism for the acid catalyzed aldol reaction. And now you can go back to each of the problems that we looked at today under base catalyzed conditions, such as this example, and try the mechanism now not under aqueous basic conditions, under base catalyzed conditions, but try to draw the mechanism for this transformation under acid catalyzed conditions, following the same steps that we just outlined in the case of the intramolecular reaction. So you should be able to draw the mechanism of the aldol condensation reaction catalyzed by both base and acid. Now I believe we have completed all of our learning goals. I believe I have one more practice question here. So here are some synthesis problems. We can take these products of the aldol condensation and draw out the starting materials from which they came. So this will be our final act of this lesson before we take some time to reflect and then move on to the retroaldol. You did notice all of these reactions, all these elementary steps I show with reversibility arrows. Oh yes, the aldol condensation can go in both directions, and you will take a look at that in the next lesson. But before we end this one, let's be sure that we can draw the reactants that would produce the following self, intramolecular, and crossed aldol products. Give it a go. Look for the beta hydroxy aldehyde or ketone, or the alpha beta unsaturated aldehyde or ketone in each of these molecules. Then disconnect between the alpha and beta carbons, knowing that the alpha carbon came from the nucleophile. Now, under basic conditions, that will be an enolate. Under acidic conditions, that will be an enol. But either way, the alpha carbon in the product came from the nucleophilic partner, and then the beta carbon came from the carbonyl form. In the case of the self-condensation, the enolate is made from the same exact aldehyde. The aldehyde and the enolate are in equilibrium with one another under the conditions of the reaction, and then they condense. That's sort of the whole point. So this just comes from butanol undergoing a self-condensation. So either aqueous base, or you don't put both on an exam, you just choose one. So basic or acidic conditions. For the intramolecular example, this intermediate would have been involved in the key bond forming step. We can go ahead and just draw the neutral compound from which this species came. So just take that enolate, put it back to the carbonyl form. And if you want, we can number the carbons and write this molecule out in a conformation in which we might more commonly draw hydrocarbons. So if you'd like to draw this out in a zigzag conformation, same deal, treatment with aqueous base or aqueous acid would yield the intramolecular aldol product. And just choose one set of conditions. In the case of the crossed aldol, we see that it's benzaldehyde plus acetophenone. And with the crossed aldol, we want to be careful, but this would be fine because benzaldehyde is non-enolizable. There are no alpha hydrogens. So benzaldehyde would just be the electrophile, and acetophenone would generate the enolate nucleophile, as shown here. Aldehydes are more reactive than ketones, so the enolate of acetophenone would only condense with the benzaldehyde. So this is a good crossed aldol. All right, so in the forward direction, this time I'm just going to write basic conditions would lead to this crossed aldol product. Great, we've done it. Don't leave quite yet. I did want to point out one weird thing on the learning goals. So where it says provide the complete curved arrow mechanism for the formation of the aldol condensation product by an E1CB. E1CB is just under basic conditions, and as we said, under acidic condition, it's just a normal E1 elimination. All right, excellent. Time to practice.